Okay, so where we left off with the last video and last lesson is we were talking about reaction types, in particular reaction types part A, where we explored our composition and our decomposition reactions. So the objective of today's lesson and video is to explain the benefits of classifying reactions and also identify displacement reactions and give examples. So the first one we're going to look through today is called our single displacement reactions. So if we scroll down slightly, what we can see here are two images of crystals of silver forming on top of copper. These images were taken when a piece of copper metal was actually placed in a solution of silver nitrate, and what resulted was these delicate tree-like crystals forming on the surface. At the same time as these crystals are being formed, this solution actually turns blue, indicating the production of these copper ions. Now down below, there is a short clip of, or it's a time lapse of US currency, so pennies in particular, which are zinc coated with copper. So I'm not going to play the video for you. You can pause this recording, jump over to your worksheet and play it through there. And after watching that, there is a space for you to actually describe what is happening in this video. So if you've watched the video, you definitely have something to write here. Now, let's take a look at this diagram here. So what's actually going on in this diagram? So on this left-hand side here, it looks as though we have a solution. So the liquid here, shown by this label, is made up of silver nitrate, which means we've got a solution of silver ions, shown by Ag+, plus our nitrate ions, NO3-. We know that they're ions because they have a charge to it, the positives and the negatives. What we also have here is a piece of copper metal. We know it's copper metal and not a copper ion because they only have the letters. There is no charge to it. So it's just Cu as opposed to Cu plus or Cu minus. So this is the solution before it reacts, so we can see up the top here. After a reaction occurs, your silver nitrate solution becomes a copper nitrate solution. As a result, we now have copper ions mixed with our nitrate ions in this liquid, this solution. We are going to have some leftover copper metal from previous that is unreacted, so they're just going to sit down the bottom as such. But now they've been coated in a silver coating. So because it's silver, it's a solid, it's going to be Ag, not Ag+, like we had as our ions. So what we can see here is that the silver and the copper have traded place. As such, what we call this is we say that the copper has displaced the silver from the solution. And this is what we call a single displacement reaction. And it's got a general form of AB plus C gives you CB plus A. Now, if we look at this reaction in this diagram, we can show it as chemical equations. So we'll scroll down slightly. So we started off with a solution of silver nitrate, so AgNO3 as a solution, so it's an aqueous. We know that because we have a solution here that is full of silver ions and nitrate ions. We've then reacted it with copper solid, so our solid piece of copper, so our copper metal shown here. And then it's reacted together to form copper nitrate, so CuNO3. So we've got copper ions now and nitrate ions in solution, so in aqueous, so in liquid, plus our silver, so Ag solid. So this solid up here. So notice how we start off with our nitrate ions, we end off with our nitrate ions. And if you really look at the two diagrams, nitrate ions really haven't done anything. So as a result, we can say that the nitrate ions, NO3-, don't actually take part in this reaction at all, and they just simply remain there. And as such, we call them spectator ions. So just like if you were to go to a sporting event or a sporting game, if you're just in the audience, you're a spectator. You're not playing the game, you're not participating in any way. You're just there watching. That's exactly what these nitrate ions are doing as well. They're just there watching it all happen. Down below here, we can see that there is a table. There are two tables of some common ions and their charges. So let's first look at our positive ions, also known as our cations. Cations being positively charged means they are ions with a positive charge. For example, hydrogen. A hydrogen ion has the charge of H+1. What that +1 means, it's that it's lost one electron, and because electrons are negatively charged, if you've lost one, you have more positive subatomic particles, so you've got more protons than you do electrons. So you are overall positively charged by one proton. So here you can see hydrogen, lithium, sodium, potassium, ammonium, and silver all have a charge of +1, which means they've all lost one electron. Moving on to the next column, we can see magnesium, calcium, barium, iron, copper, zinc, and lead. They all have a charge of +2. What this means is that they've lost 2 electrons and overall have a charge of +2. So they have 2 extra protons than they do electrons. So more positives than negatives. In this third column, we've got aluminium and iron. As you've guessed, they have a charge of +3, which means they've lost 3 electrons, so are overall positive by 3 protons. So these are all positive ions, so they're cations. But if we now look at our negative ions, you've got your anions. What this means is that these atoms have gained electrons, and as such, by gaining an electron, they are now overall negatively charged. So this first column here, so chloride, bromide, fluoride, iodide, hydroxide, and nitrate, they all have a charge of -1 because they have gained an extra electron, which has made them overall negatively charged. With your second column here, your oxides, sulfides, carbonates, and sulfates all have a charge of -2, so the 2-, and like you've probably guessed, it means that they have gained 2 electrons. So they have more negative charged particles than they do positive. Now, based on all that information that we've just gone through, that leads us to a few questions, just a few review questions about that theory. Now, this first one here. Applying the form AB plus C gives you Cb plus A to the silver nitrate copper reaction, which is this one up here. What does B represent in this case? Keeping in mind that the B doesn't appear to be the one changing. It's the A and the C that are making that swap. Now, with what we now know about what doesn't change, we actually call them our spectator ions. So in this particular case, the spectator ions are your nitrate ions because they, if we scroll back up here, the nitrate in both cases, they don't do anything. They still remain the same. They're just there watching. And with the information we're told here, notice the nitrate ions don't take part in the reaction, but simply remain. As such, they are called spectator ions. So your nitrate, shown by NO3-, is your spectator ions that are represented by B in this particular general form. Moving on to question 3. Why are the nitrate ions in this reaction called spectator ions? I've just about touched on that earlier. So if you remember, write that one down. If not, pause the video, have a think about it, or just rewind slightly. But what you should get for that is that your nitrate ions are spectator ions because they take no part in the reaction. They simply remain as ions in solution looking on, while the copper displaces the silver. So think back to my audience analogy. If you're in the audience, you're just looking on. You're not contributing to it. For question 4, here we have a diagram, and we're told with the instructions, when zinc metal is placed in a copper sulfate solution, a displacement reaction occurs. Use the equation to label the diagram and move all of the atoms and ions into their correct places. Now, the equation that they're talking about is this one up the top. We are told that we have a solution of copper sulfate. We know it's in solution because it's aqueous. We know it reacts with a solid piece of zinc, so solid S, zinc, to form a solution of zinc sulfate, so ZnSO4. We know it's solution because of the AQ, plus copper solid. Let's start by labeling our solutions themselves. Now, think of it this way. Everything on the left-hand side of this arrow happens before the reaction. Everything on the right happens after the reaction. So let's start with the before. What we start with is copper sulfate solutions. So we know this solution is going to be copper sulfate. So given the options for our labels here, we can find one that says copper sulfate solution. So we'll just pop that in that box available. Now, because we know it's a copper sulfate solution, now we have to add in our ions. Down below we can see we have our sulfate. So let's go ahead and add 3 of them in. In a solution, there are many atoms of ions. Many ions in solution, sorry. But in this particular case, we're just going to go with 3 to make it easier. So we know we have sulfate. We also know we need copper. Now, the question is, do we need solid copper or do we need copper as an ion? The trick here is we know copper is in solution, so it has to be in ion form. So in the ion, we'll just drag 3 of these in as well. Now, for our reaction, we're told that our copper sulfate solution is added or reacts with a solid piece of zinc. So this label here points to this block. So we're just going to go ahead and call that our zinc metal. And once again, is it a zinc solid or is it an ion? We know it's a solid because of this denotation up the top. So we will go ahead and let's pop 3 of these atoms here, just to make it clear. Now, all of this is what happens at the start, so before the reaction occurs. After the reaction occurs, we know that we are left with zinc sulfate in solution. So this solution is made up of zinc sulfate. So we're going to go ahead, and pop this icon here. So a solution of zinc sulfate. We know we have sulfate, so we're going to go ahead and drag 3 of these in. And we know we need our zinc ions, so we'll pop 3 of these in as well. Now, here we know that from the equation we end up with a solid piece of copper. So the only option available is our solid metal, which is our copper metal. And this grayish, orangish block, we are going to call our copper. So once again, we'll pop 3 of these in. We know they're solids because they have no charges. So there you have it. Using a description and a chemical equation, you have gone ahead and described a diagram from this information. Now, all of this work that we've done so far has been on single displacement reactions. Now we move on to slightly more conceptually difficult reaction, which is a double displacement reaction. So, a different type of displacement reaction can occur when 2 solutions are mixed together. These are known as double displacement reactions, and they have the following form. AB plus CD gives you AD plus CB. What happens here is that the reactants, so what you start with, are both aqueous in solution, in which the positive and negative ions are dispersed in water, so they're mixed with the water. When these 2 solutions, so AB plus CD, when they're mixed together, their ions are free to move around and react with each other to form new compounds. For example, what's happened here? We've got silver nitrate in solution plus sodium chloride in solution. These ions break apart, they mix with the water, and then they react to form silver chloride, solid, plus sodium nitrate in solution. So once again, we've got the word equation up the top and the chemical equation down below. If we look at this image on the side here, we can see that a silver chloride, which is a white solid powder shown by the little swirl, is produced in this particular double displacement reaction. So what's the most important thing here to take away is that silver chloride is a solid that's mixed amongst all this other aqueous solution. Now, keeping all of that in mind, in this above reaction, why do the silver ions form a new compound with the chloride, but not the sodium ions? Now, before you have a think about this, because they are all in ions, so silver, chloride, and sodium, what I want you to do is scroll back up slightly and take a look at this table here. So, pause this video here, take a moment, read through the table, read through the question again, and have a guess or have a hazard as to why that is the case. When you're ready, you can continue playing to hear more about it. So, based off the question itself, it tells us that the silver ions form a new compound with the chloride ions. So silver is down the bottom. So silver ions react with our chloride ions here to form a new product. Whereas the silver ions do not react with sodium ions here. Now the reason for that is sodium has a charge of +1, so positive. Silver has a charge of also +1, whereas chloride has a charge of -1. Just like with a magnet, when you put two magnets with the same end pointing at each other, what's actually going to happen to them? What they're going to do is repel, so they're going to move away from each other. So silver and sodium, both having that positive charge, are not going to react together because they're actually going to move in opposite directions, move away from one another because of that same charge. Whereas when silver comes in contact with the chloride, the positive and the negative, what actually happens is they attract to one another. They're attracted to one another. As a result, they can react, and what we get is our silver chloride solid. So it's what we call a precipitate. So with what I just explained, that's all just here. The silver ions and sodium ions both have positive electrical charges, so they repel each other, whereas the silver ions and the chloride ions are different, they're opposite, so they are attracted to one another. Moving on to number 6. What products might be formed if you mix solutions of lithium hydroxide with iron sulfate? So, with a double displacement reaction, what we are going to end up doing is keep the first half of each of these reactants the same, but the second halves, we're just going to swap them over. So it goes from silver nitrate to becoming silver chloride, so as shown here. And it goes from silver chloride to comes from sodium chloride into sodium nitrate, shown over here. So it's important that we don't end up calling it silver chloride and nitrate sodium, because that doesn't exist. To name it, we always put the metal first. So sodium is a metal, so is silver. So to name it, it's silver chloride plus sodium nitrate, as shown as such. Now, keeping that in mind, given this reaction, lithium hydroxide and iron sulfate, keep the first half of both, swap the second half, you end up with lithium sulfate plus iron hydroxide. Looking at the options that we have here, does that exist? It is this second one here. So we'll go ahead and select that option. Now, question 7. You are asked to briefly summarize the difference between single displacement and double displacement reactions. So, with a single displacement reaction, what we can see here is that one of the ions swap over. So, in a single displacement reaction, an element trades place with another in a compound, making a new compound. Whereas with a double displacement reaction, it involves ions from two compounds trading places to make two new compounds. So this compound is different to this one, which is also different to this, which is also different to this. So you get two brand new compounds. Now, as a final question for our displacement reactions, so single and double, let's take a look at this little summary. So, what you've been asked to do here is create a summary of the 4 types of reactions we've studied this lesson and last lesson. This first one here, where you've got A plus B gives you A plus B. A plus B gives you AB. So you're going from 2 or more reactants to give you a single product. So if you think back, that is actually an example of a composition reaction, so combining reactants together. Now we need to look for an example. So, out of the 4 examples available to us, the only option that suits is this first one here, where you've gone from 2 reactants to a single product. Every other reaction has more than one product, so we know it cannot be a composition reaction. This second one here, we've gone from AB gives you A plus B, effectively the opposite of our composition reaction, which is our decomposition reaction. As such, we're looking for a reaction that breaks down. So you're going from a single reactant to multiple products. Now, the only option available is this one right here, where you've gone from one reactant into multiple products. Next, we move on to AB plus C gives you CB plus A. That is the general form for a single displacement. So we'll go ahead and move that one over. Now, the example here of a single displacement is actually going to be this one. The reason for this is the iron has swapped with the carbon. That's all it's done. The iron has swapped with the carbon. Whereas this last one here, AB plus CD gives you AD plus CB. That is an example of a double displacement, whereby the appropriate example is this one right as such. Now what you've just done is create a summary of the 4 types of reactions that we have covered over the past 2 lessons. So, moving on into some slightly more conceptually challenging questions. Question 9 asks you, imagine you live in a society which until now has had plentiful supplies of 2 liquids, pentane, C5H12, and hexane, C6H14. Both burn well, releasing a lot of heat, and are used as fuel for heating, cooking, and industry. Equations for the combustion of the liquids are as follows. We've got pentane mixed with oxygen, which gives you water and carbon dioxide, and hexane plus oxygen gives you water plus carbon dioxide. With pentane and hexane resources running low, prospectors have found sources of a new liquid, heptane, C7H16. The chemists say that the new liquid is a good candidate to be used as a fuel replacement because it will burn in a similar way to the existing fuels. Now, here are your questions. Question part 1. Why do you think the chemists make this prediction? And part 2. Use this example to explain one advantage of classifying chemical equations. So, take a moment to look at your 3 liquids, pentane, hexane, and heptane. Look at what they are all made up of. Pentane, hexane, and heptane are all made up of only carbons and hydrogens. The only difference between the 3 of them is how many carbons, how many hydrogens. As such, for number 1, what you could say is, chemists would make this prediction right here, because heptane is made up of the same atoms, carbon and hydrogen, as pentane and hexane are. So because they're made up of the same components, it's a worthwhile prediction to say, because they're made up of the same components, chances are they will react in a similar manner, or they will behave in a similar manner. It's not to say they are exactly the same, because they're not, but they may have some overlapping traits. Question 2 here. Use this example that we've just talked about to explain one advantage of classifying chemical reactions. Now, before you all start thinking outside of the box and stressing out, this question is fairly simple. An example of an advantage is that chemists can actually make these predictions by actually being able to classify chemicals into different groups and different reactions into different groups. Chemists can make predictions. Okay, if liquids with carbon and hydrogen are good for heating, cooking, and industry as fuels, no matter how many carbons or hydrogens there are, it will still be a good fuel. So by classifying it into the same group, they can make these predictions for these reactions that belong to these groups. Now for some revision. So based off these 2 lessons of work, what you should now be able to do is answer these following questions. So the first one here. Classifying chemical reactions helps us to. Sometimes there may be multiple answers that are correct, so it is your responsibility to go through your work and just double check. But in this particular case, I would select these 3 because we know, based on the previous question alone, we know it's these bottom 2, so make predictions about reactions and also explains the reactions, but it also produces useful materials. So if we just show our answer, it'll just double check and confirm that. Question 11. What is the general form of a composition reaction? Remembering composition means combining together. So we've got option A plus B gives you AB. That looks about right. Let's tick that for now. Could it be A plus BC gives you AC plus B? Well, no, because that is an example of a single displacement reaction. Could it be C? AB gives you A plus B? Also no, that is a decomposition reaction. And this last one here, A plus BC gives you BC plus A. Well, that's also an example of a single displacement reaction, so that cannot be the case. As such, the only viable option is A. A plus B gives you AB. Moving on, we've got question 12. The metal sodium reacts with chlorine gas in a composition reaction. The product is most likely to be A, B, C, or D. The easiest way to come about this is, let's look at the info we're given. We know we have sodium, we know we have chlorine gas. It's a composition reaction, so they're joining together. So, we know it cannot be iron oxide, because nowhere in this question does it mention iron or oxides. We know it cannot be sodium hydroxide, because nowhere does it mention a hydroxide. And we know it cannot be a hydrochloric acid, because nowhere here is there an acid. As such, the only viable option is going to be sodium chloride. Moving on, for number 13, which of the following are decomposition reactions? So, keeping in mind decomposition reactions start with one reactant and it breaks down into multiple products. So, let's look at the options that have one reactant first. So, A does, B, not C, because there's 2 there, and D. So far we've got these 3. Now, as a decomposition reaction, we know it forms 2 or more products. Now, here we've got 2 products, which looks good. Option B also has 2 products. And option C also has 2 products. So by deducing all of that information, I think it's safe to say let's lock in these answers and let's double check. So yes, because we've gone from a single reactant to multiple products, these 3 options here are your decomposition reactions. Moving on to question 14. If you add magnesium powder to copper sulfate, a single displacement reaction occurs to produce some of these four options. Now, we know we have magnesium powder. We know we have copper sulfate. As a result, because it's not a combination reaction, we know our final product cannot only be one compound. So that automatically rules out option A and option D. And we're left with two options here. Now, as a single displacement reaction, what's going to happen is your sulfate stays the same. Remember, your sulfate it's a spectator ion. And as a single displacement reaction, your magnesium is going to displace the copper. So they're just going to do a bit of a swap. As such, what you will end up with is copper, solid copper, because that's the copper's kicked off here by the magnesium, and the magnesium takes its place. So you've got copper plus magnesium sulfate. And out of these two options here, this one fulfills that. So you've got magnesium sulfate solution plus copper metal. So if we check our answer, that confirms it there. Question 15. Which of the following worded equations describes a double displacement reaction? Now, remember, double displacement, keep the first half of the name, swap the second half over. Now, let's look at this first one. Magnesium nitrate plus sodium hydroxide. Keep the first half, swap the seconds. So magnesium becomes magnesium hydroxide. Yep, that looks good so far. Then we've got sodium nitrate. So this is a viable option. So let's hang on to that for now. Let's double check our other options. Magnesium carbonate forms magnesium oxide and carbon dioxide gas. We know it cannot be this because that is a decomposition reaction, so it breaks down. So we rule out B. We move on to C. Methane gas plus oxygen gas gives you carbon dioxide gas plus water vapor. So keep the first half, swap the second half. So we've got methane, and none of our options on your products have methane. So that rules out that option C. And lastly, we've got copper oxide plus carbon reacting to give copper metal plus carbon dioxide gas. So keep the first half, swap the second. So copper becomes copper, and that cannot be fulfilled because that product does not fulfill our requirements for double displacement, so we ignore that one. So the only viable option here is option A. Now, for question 16. Many sulfides are important sources of metals. For example, we obtain lead from the mineral galena, also known as lead sulfide, and silver from the mineral argentite, also known as silver sulfide. These minerals often form in a similar way. When dissolved metals react with sulfide ions in hot water flowing through rocks. Now, the question asks us, why do we think it's useful to group these reactions together as a single type? Please write 2 sentences as a minimum. So pause this video, look through some of the work we've already done. In particular, maybe focus on question 9. Have a read through of that, see if any of that can be applied here. So take a moment, pause this video and read through it, please. Okay, so hopefully you've had a minute to read through it. So, what we're looking for question 16 here is that by grouping these reactions together as a single type, we can gain a better understanding of the natural processes that lead to the formation of sulfides. We might find that the different sulfides form in similar conditions, or that there are interesting differences between them. Whatever pattern we find will help us to search for economically valuable deposits, also known as ores, that could be used to extract these metals. It might also allow us to predict the possibility of similar reactions involving other metals, with potentially useful applications. So, moving on to question 17. It's a two-part question. First part, explain the difference between composition and decomposition reactions in terms of their general forms. Please write 2 sentences as a minimum. So what we're looking for here is what we already know about composition and decomposition reactions. So take a moment to pause this video and write what your understanding is. Okay, so by now you should have written something about composition and decomposition reactions. So, what a composition reaction is when 2 or more reactants join together to form a single product. Its general form is A plus B gives you AB. Whereas a decomposition reaction is one when a single reactant breaks down into 2 or more products. Its general form is AB gives you A plus B. Now, here comes part 2 of this question. Apply the distinction from above, so from part 1, to the Haber process for the formation of ammonia and its reverse reaction, using worded equations to illustrate this. So, if you've forgotten about the Haber process, pause this video, open up yesterday's work on reaction types part A, and we can go through the Haber process again. But what we're looking for part 2 is that the Haber process is an example of a composition reaction, as it forms a single product out of 2 reactants. So the word equation here is hydrogen plus nitrogen gives you ammonia. Now, you're also asked about the reverse reaction. The reverse reaction is an example of a decomposition reaction, as it forms multiple products from a single reactant. Single reactant, multiple products of hydrogen and nitrogen. Now, the last question here, question 18. Why is the following reaction classified as a single displacement reaction? The reaction is iron sulfate in solution plus zinc solid gives you zinc sulfate in solution plus iron solid. So, chemical equation, word equation. So, describe what happens to the iron, zinc, and sulfate during this reaction. Well, first of all, we're told it's a single displacement, and we know it's a single displacement reaction because the iron and the zinc, they swap places. So the iron comes along, the zinc comes along, boots off the iron, and now forms a solution with your sulfate, and your iron that was booted off now forms a solid. So it just swaps places. Now, so we've talked about what happens to the iron and the zinc. So they just swap places and they are displaced. Whereas the sulfate, what is happening to the sulfate on the left and the sulfate on the right? Nothing. The sulfate in this case is doing absolutely nothing. So if you remember the word for the ions that don't react, it's what we call our spectator ions. As such, a model response could be as such. This is a single displacement reaction because the two metals, iron and zinc, swap places. The iron moves out of solution to form a solid, while the zinc moves from a solid into a solution. The sulfate ions, however, simply remain in solution. They don't take any part in the reaction, and as such, they are called our spectator ions. So, question 18 wraps it all up. The very last thing is a bit of a reflection in terms of 3 things that you were interested with today's work. After you've done your little reflection, where my mouse is right now, you should see a little blue box on your screen when you do the work that says, "I'm finished, show my teacher." Be sure to fix up all your answers and then hand it in to me so I can go through it and just double check that for you.